Hello class, welcome back to EX 376. Today we're going to be talking about Turing reducibility. I promise it's not as scary as it sounds. Let's jump right into it. So A is Turing reducible to B if it's possible to build a decider for A given a decider for B. So we're saying, okay, we have the right-hand side's decider. Can we build a decider for A? It doesn't matter if this is not actually decidable or not. We're going to say, okay, we have this decider. I know that's a little bit foggy, but let's go through an example and hopefully that'll clear things up. So here we have the two languages, LAccept and LHalt. LAccept is the set of all Turing machines and inputs of set Turing machine M accepts X, and LHalt is the set of Turing machine and inputs where M halts on X. So this means that it either returns true or false. It either accepts or it either rejects if it's in LHalt. If not, then our Turing machine just loops on X. Let's show that LAccept is Turing reducible to LHalt. So again, we have a decider for the right-hand side. Can we make one for the left hand? So our strategy is to assume, again, a decider for LHalt, build one for LAccept. This is helpful when I took the class. Reject can be thought of as returning false and accept as returning true. And all of these deciders are Boole functions. You can think of this as a Boole function that takes in an input and returns true or false. So we want our Boole function here to return true if M halts on X, and we want it to return false if it doesn't. So again, we have our decider D and LHalt. We want to see, okay, does MX, does our input we pass into here exist in LHalt? Does M halt on X? So if D M X accepts, then what does that mean? It means that M halts on X, so it either returns true or false. If it returns true, we can return true. And if it returns false, we want to return false. So we would return M of X. So this is like our Turing machine M, and we pass in X. And then else, this means that we the decider D rejects on MX, and this means that we loop on X. So this means that we cannot return true since we do loop, and we are going to reject. So let D be a decider for LHalt. Now we're going to write it into words. Here is like our little function version of seeing it. Now let's write it formally. Then a decider for D prime for LAccept would be to run D on input MX. If it rejects, then we do not halt, then we're going to reject. Otherwise, so this means that M does halt on X, we're going to run M on input X and return the same. So now we should look at correctness. Does this actually work? If D rejects, then M loops on our input X, so M cannot accept X, so D prime rejects. If D accepts, then we know M halts on X, so we can run M on X and accept if M accepts X, reject if it doesn't. So because we showed, okay, if M accepts X, then D prime accepts, otherwise we reject for every case. And we showed that this was given our decider for LHalt. This means that LAccept is Turing reducible to LHalt, which is what we want. So what we did is we said, okay, we have a decider for LHalt. Oh, my bad. So we have a decider for LHalt, which would be B. We built a decider for LAccept, which is A. So LAccept is indeed Turing reducible to LHalt.